This is a practice exercise from page 187 of the textbook. It's using Hess's law in a slightly different way in order to calculate enthalpy change for an entire reaction based on the enthalpies of formation of the individual compounds in that reaction. So the equation we're going to want to keep in mind is that the enthalpy for the reaction is equal to the sum, so it's a sigma, that's a sum, the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So we've got products minus reactants, remembering that products are here and reactants are here. The other thing that's going to be important is that the mole ratios matter. So if I've got 2 moles of carbon dioxide, I need to double whatever the enthalpy of formation is for carbon dioxide. So if I just write this out in symbols, that means that my delta H for the entire reaction is going to be equal to 2 times whatever the enthalpy is for carbon dioxide gas plus 3 times whatever the enthalpy is for liquid water. And that whole quantity is going to be subtracting the enthalpy for C2H5OH as a liquid added to 3 times the enthalpy of formation for gaseous oxygen. So then we want to look at this table, table 5.3, to find all those values. So carbon dioxide as a gas, that's going to be right here, negative 393.5 kilojoules per mole. For water, that's going to be down toward the bottom, and we want to make sure we've got liquid water, and so down there it's going to be negative 285.8 kilojoules per mole. And then we're going to find the ethanol, C2H5OH, which is negative 277.7 kilojoules per mole. And notice that since these are in units of kilojoules per mole, that's why we need to use the molar coefficients, because if this is kilojoules per mole, but I've got 3 moles, I need to make sure I'm using that factor of 3. Now if you try to use this table to look up the enthalpy of formation for oxygen, you're not going to find a value. And that's because O2 gas is the standard state of oxygen, which means that its enthalpy of formation is 0. It's not that it's missing, it's not that you can't continue, it's that it's 0 because this is an element in its standard state. So we won't need to worry about that when we do our calculations. So let's go ahead and set this up with actual numbers plugged in. So this is going to be 2 times negative 393.5 kilojoules plus 3 times negative 285.8 kilojoules, all of that, minus negative 277.7 kilojoules plus 0 kilojoules, because remember that oxygen's already in its standard state. So if you do this math, do all the calculations, we're going to round this to 4 significant figures because that's how many significant figures we had in all of these values, and you should get an answer of negative 1,367 kilojoules for this entire reaction. So it's really a pretty straightforward calculation, just making sure you're doing products minus reactants and you're using the mole ratios when you perform the calculations. Now if we take a look at the second part of this problem, this is a little bit different. In this case, they're giving us the enthalpy change for the entire reaction, and they're asking us to solve for the enthalpy of formation for a single substance. So again, let's set up what this looks like just with symbols, and then we can figure out where all the missing information goes. So we know that the delta H for the reaction is equal to the sum of the enthalpies of formation of the products minus the sum of enthalpies of formation for the reactants. And since we don't have any coefficients in this equation, it's just going to be 1 mole of CuS plus 1 mole of liquid water, and from that we are going to subtract 1 mole of solid copper oxide and 1 mole of hydrogen gas. Okay? Now again, if we look at these, we should see that some of these are going to be pretty easy. They are going to be 0 because we've got elements in their standard state. Copper, metal, and hydrogen gas are in their standard state. And if I start plugging in the numbers that I know that the overall enthalpy of this entire reaction is negative 129.7 kilojoules. I know that's going to be equal to whatever the enthalpy of formation is for liquid water, and I've looked that up earlier. So this is going to be 0 kilojoules, because copper is a solid, plus the negative 285.8 kilojoules. So that entire thing, we're going to subtract the enthalpy of formation of CuO, solid, because we don't know that yet, that's what they're asking us to find, and then this is just 0 kilojoules. So essentially we have almost all of the information here. Doing a little bit of simplification, that means negative 129.7 kilojoules is equal to negative 285.8 kilojoules minus whatever the enthalpy of formation is for copper oxide. So rearranging that equation, you should find that the enthalpy of formation for CuO is just the difference between those values, which is negative 156.1 kilojoules. So we're using the same information as the first half. In this case, instead of solving for the final total enthalpy for the reaction, we're just solving for the missing piece. And again, something that's really important in these is that if you ever think you're missing information, it's likely that you just have elements in their standard state and that their enthalpies of formation are 0. So you're not missing information, you just need to remember that for elements in their standard state, the enthalpies of formation are equal to 0. If you remember that, these calculations should be pretty straightforward once you have the setup in front of you and the table where you can find all of your values. Just make sure you're paying attention to your signs, including negatives where you need them, and performing your calculations with the correct number of significant figures.